Now let's actually use those relationships that we learned earlier to solve some more complex problems. So again, they're going back to review a few. We have what's called the reciprocal identities. And I already alluded to you that you have sine, cosine, and tangent. And now you can take the reciprocal of sine to get cosecant. Reciprocal of cosine gives you secant. And reciprocal of tangent gives you cotangent. So you can just simply reciprocate one to take the reciprocal of one to get the other ones. Now, using these properties, these are very, very fundamental problems at first. And then we're going to expand, make them a little bit more challenging. Letter A simply says, if you know that the secant of this angle theta is 5/3, what would be the cosine of that same angle? Well, looking above, we see that, hey, cosine and secant are simply reciprocals of one another. So if the secant of theta is 5/3, the cosine of this same angle must be the reciprocal, or 3/5. Don't make a wild animal out of some of these problems. Letter B, I kind of disagree with from the author of your book. He's trying to trick you. He's trying to give you a radical that's not simplified for whatever reason. You would think that if he's giving me a radical, he'd have it simplified. So we're going to take the extra step here at first and go ahead and take what he's giving me, and we're going to go ahead and simplify it first. So we know that negative root 12 over 2 is the same thing as what? Well, root 12 is 2 root 3, right? And our 2's would cancel out. So what he's technically giving me is negative root 3. That's it. We're being told that the cosecant of this angle is negative root 3. We're being asked to come up with the sine of it. So the sine and cosecant are reciprocals. We're going to take negative root 3, come up with the reciprocal, which would be negative 1 over the square root of 3. And then I got to rationalize the denominator and get negative root 3 over 3. There's the final answer that we're looking for. So if you simplify it up front, it makes it a little easier problem later on. Okay? Now, the very first page, those first 3 problems that we were working with. Let me go back and make reference to those one more time. Here we had a case where the angle that we are working with, theta, ends up being in the first quadrant, the upper right-hand quadrant. And as you can see, all 6 trig identities, trig functions with this problem, all ended up being positive amounts. Why is that? Well, when you're in quadrant 1, number 1, r is always positive, always positive. But in quadrant 1, your x-coordinate's positive, your y-coordinate's positive. So when you form all 6 of these, you're constantly taking positives divided by positives, which gives you positives. Look at quadrant 2. Or quadrant, in this case, quadrant 3. In this case, we're in quadrant 3, where this guy's negative and this guy's negative. So every single trig function except tangent, y tangent. Tangent, we'll end up taking y divided by x. We'll end up taking negative divided by negative, which gives me positive. That's the only case where that's happening. Negative divided by negative is positive, and also it's reciprocal. But notice all the other ones, since the numerator, in talking numerator-denominator, one's positive, one's negative, you're always going to end up with a negative number. So we can summarize that in the following chart. In terms of, if I talk to you about a quadrant now, where are your trig functions positive or negative? Well, in quadrant 1, all of them will be positive, all 6 of them. Now when I say all 6, we can condense that by me saying all 3 of them, and it's given that their reciprocals are going to have the same sign. But in quadrant 1, all of them are positive. Quadrant number 2, the sine and its reciprocal are the only trig functions that kick out a positive number. Quadrant 3, tangent and its reciprocal are the only functions that's going to give you a positive number. And quadrant 4, cosine will end up being a positive value.
I remembered it by putting an A as TEC and then all students take calculus.
That's the clean version. Yeah, I taught the trig last semester, and you just imagine the sayings that I started hearing, which I don't want to repeat some of them, but you come up with your own way of remembering that and what he said, he was taught in high school, all students take calculus is a way of coming up with simply remembering which quadrants have that, whether they're trig function or which angle has a positive or a negative trig function, okay? Because knowing what quadrant you're working in, and then that leading into telling you if your trig function's positive or negative, could save you a lot of steps with some more advanced problems coming up in future sections. Okay? Moving on. Also for your trig functions, talking of range, remember domain and range of a function. Domain means those are the values that are going into the function. Range values what's coming back out of the function. And you saw a minute ago that with the quadrantal angles, let's just talk about sine. We started sine of 0, and then as we went counterclockwise, we went from 0 to 1, back to 0 again, to -1, back to 0 again, back to 1, back to 0, back to -1. Every time I go around the circle. So the numbers that come out of the sine function, the range of the sine function, and also cosine, will always be between -1 and +1, as you saw up here with our diagram. As I spin around the XY plane, in terms of 0 degrees to 360, and I keep going, no matter what I use, I'm always going to get values between -1 and +1. The tangent of an angle and also its reciprocal cotangent, the range of those functions, you can get anything. Any real number can come out of those functions. And if we take a look at the reciprocal of sine and reciprocal of cosine, it's kind of like the opposite. If sine has to be between 1 and -1, then its reciprocal can be anything but that. It's everything but that. So it can be less than -1 or greater than +1. Likewise with reciprocal of cosine. It's everything but what sine and cosine was kicking out. So all I want to know here for A, B, and C, are those statements possible, yes or no? Just simply take a glance at them and jot down whether you think those statements are possible or not. And if you don't think they can be possible, which one up here which rule up there is being proven false. How about letter A? Possible or not? Not possible. Why not possible?
It's above 1.
Square root of 8 is greater than 1 if you were to convert that to a decimal, so no, not possible. Sine of an angle must be between 1 and -1. How about B?
Yeah.
Absolutely. Yep. The tangent function can kick out any real number, so you're okay there. And how about C? No. 0.6 is between -1 and +1, and notice that the secant of an angle can never be between those two values, so simply not possible. All right. More complex question. Our example says, suppose that I hand you this angle theta, and I'm telling you up front it's in quadrant 2. I'm also telling you that the sine of this angle is 2/3. Find me the values of all the other trig functions. I recommend highly, if they don't provide you with a picture, draw a picture as to what's going on with this problem. Draw actually an actual picture of the angle that's in question. So here's the XY plane. I'm going to construct this angle or draw this angle that's in quadrant 2. So there's the initial side. I know I'm over here somewhere in quadrant 2. Here's the angle theta in question. Over here in quadrant 2. And I know that the sine is 2/3. I'm being told that sine, which we know is y over r, is 2/3. So I'm going to pick this point P again. Pick any point P on the terminal side. It has associated with it a vertical distance from the origin and a horizontal distance from the origin. We know that r is 3. R value is 3. And we know that the y distance is 2, or the y coordinate is 2. We got to come up with the x coordinate, right? We got to come up with the x coordinate. So I'm going to modify. I know that r can be found by taking the square root of x squared plus y squared, and I need to modify that to find x. Turns out that x, if you take the equation that I just wrote, square both sides, subtract y squared, then we turn around and take the square root again. X can be found by taking the square root of r squared minus y squared. So x will be the square root of r, we know is 3. 3 squared is 9. Y is 2. Y squared would be 4. So it looks like x is going to be the square root of 5. So there's our coordinate of our 2 points, or the coordinates of our single point. Point P is located at x comma y, which is the square root of 5 comma 2. I think you guys can finish the problem from this point on. Now that I have x, now that I have y, and now that I know that r is 3, right? Using those 3 values, you can come up with your 6 trig functions, right? Okay. These 3 guys right here, what we're going to call the Pythagorean identities, are huge. I would get to try to memorize these as soon as possible. I'm not saying you're going to need to know them, for the next couple of days or so, but as you use, they're going to start showing up more frequently when we start proving things later on in the course. Somehow it's true that if I take for any angle theta, turns out that the sine of that angle squared plus the cosine of that angle squared is equal to 1. Now a notation hurdle that we'll jump over really quick. If I want to say I want to take an angle and take the sine of that angle and square the results, you would think that it would be written like this: sine theta that quantity squared. So if you ever want to try to write that in trigonometry, we simply write it as sine squared theta. So those two mean the same thing. It's the notation that we use if we want to square the sine of an angle or the square the tangent of an angle. So this is the way that you'll see it written. So somehow it must be true that for the same angle theta, sine squared plus cosine squared is always going to give you 1. Let's take a look at why that's true. We know that sine, right? Sine is y over r. So think of that y over r squared. And cosine squared is x over r. We're going to square that, and somehow this has to equal 1. Is that a true statement or not? Well, up top we have what? Y squared over r squared. We square the fraction. Here we're going to get x squared over r squared. And how is this equal to 1? Well, we can think of 1 as being r squared over r squared. And we know that x squared plus y squared is in fact equal to r squared, using our Pythagorean or distance formula from before. Another way of looking at that, I don't know if that was quite so clear as how the textbook, let me look at it another way. If if we take the fact that we know that r squared is equal to x squared plus y squared, we know that's a true statement from our very first picture that I showed you. If we take that equation, and I think the way the textbook, now that I remember, looks at that is if we start with that equation, let's divide everything by r squared, which is a legal step. Divide both sides of the equation by r squared. What happens? R squared over r squared becomes 1. X squared over r squared is the same thing as x over r squared, plus y squared over r squared is the same thing as y over r squared. This is cosine squared, and this is sine squared, again showing you that sine squared plus cosine squared is equal to 1. Okay? For the other two, we'll only do one of them. For the other two, let's start, and I don't know which one is going to happen here, but again, if we start with x squared plus y squared equals r squared again, and instead of dividing everything by r squared, let's divide everything by something different. Let's try, let's divide everything by y squared. Which one do we end up with? Well, what's x over y? Not x squared over y squared. What, out of the 6 trig functions, which one was x over y?
Cotangent.
Cotangent. So x squared over y squared is cotangent squared. Y squared over y squared gives you 1. And what is, not the really weird scribbly line that just came out there out of blue. What is r over y? Well, y over r is sine. What's the reciprocal of sine? Cosecant. So r squared over y squared ends up being cosecant squared. So that one comes, which one did I just show? This one right here, right? Just showing you where they're coming from. I think on the cover of your book, correct me if I'm wrong, your front cover of your textbook, are those 3 listed there for quick reference. I think on the front cover of your book you'll find, or the back cover of your book, somewhere those are handy.
We only have to know the first one, because if you just divide by sine theta squared, then you get the second one, or the, well, if you just divide.
Absolutely. You can derive the 2 from the first one. You're going to be okay with the problems that you're getting here in the next couple of days. But when we start into chapter 5, when we're going to verify trig identities, you can eliminate maybe 4 or 5 steps in that problem by using the other 2. So it is kind of handy just knowing that the 3 are, and what you're answering is, can you derive the other 2 from the first one? Absolutely. But it's going to save you some time later on if you kind of know all 3 of those ahead of time. Are they somewhere in your cover of your book, front or back? Back cover of your book? Okay. Here are our 2 quotient identities that you and I have already discovered. We know that sine divided by cosine is tangent. And we know that cosine, or let's do the reciprocal of both sides now. Take the reciprocal of this side, we get cosine over sine, and the reciprocal of tangent is cotangent, so both of these hold true. Sine divided by cosine is tangent, and cosine divided by sine is cotangent. I'm going to walk you through the first example. I'm going to have you guys try the next example on your own. These examples can be done 2 ways. One way is use the old method that you and I did at the beginning of the lecture. The second way that we can do these problems is use those 3 Pythagorean identities that I just introduced to you. And I'm going to leave it completely up to you which method you prefer. I'll walk you through both ways. It says here, our first example, find me only the sine and the tangent if you know that the cosine of this angle is negative root 3 over 4, and you also know that theta is in quadrant 2. So I'm going to go ahead and draw a quadrant 2 angle. So over here where you're located, terminal side, or initial side and terminal side, here is some angle in question, theta. And over here is this point P somewhere. And we're told that cosine is negative root 3 over 4. And I'm going to remind myself, hey, cosine is x over r. R is always a positive amount. So my r value is positive 4. And I know that the horizontal distance from the origin to that point P is technically negative root 3, meaning we're going root 3 units in the opposite direction. I know that the x coordinate is negative root 3. So I'm just treating this problem the way, like the first 3 problems that you and I talked about. How do I come up with the y? I got r, I got x, all I need is y. So we know that y is equal to the square root of r squared minus x squared. So y would equal the square root of 16 minus negative root 3 squared is 3. So 16 minus 3 is 13. So y is the square root of 13. And I can come up with all 6 of my trig values now. I got x, I got y, I got r. I need sine and tangent. Actually, I don't need all 6, right? They're specifically asking for sine. Sine is y over r. Y is the square root of 13. R is 4. Root 13 over 4. Does it also make sense why your sine function's positive? Remember that all students take calculus, right? What quadrant are we in? We're in quadrant 2. All students, right? It makes sense that sine should be a positive value in quadrant 2. How about cosine? Cosine is, I'm sorry, we already have cosine. They want tangent now. Tangent of this angle is y over x. Y is root 13. X is negative root 3. Can't leave a root 3 in the denominator, so we're going to multiply top and bottom by root 3. So we end up with the square root of 39 over 3 negative. Root 13 times root 3 is root 39, which can't be simplified, and you have your 3 in the bottom. Makes sense that my tangent's negative because the only quadrants where tangent is positive is 1 and 3. So it makes sense that the tangent ends up being negative, okay? So I treated this problem no different really than the first 3 problems we did, which doesn't matter to me. Now, Mr. Who wrote our book, Lyle, Hornsby, and Snyder, this example in their textbook, they treated it a whole other different way. I'm telling you, you have this option if you want to treat it like all of the other problems that we did earlier. The other way they like to look at this problem is not by using a point P and not by coming up with the missing coordinates. They say, well, you can go ahead and use your Pythagorean identities that you just learned. So if we start with the fact that we have, we know that sine squared plus cosine squared is equal to 1. Let's fill in what we know. We're given cosine theta. And that means that cosine squared theta would be equal to squaring both sides. Negative root 3 over 4 times negative root 3 over 4 would be positive, what? 3/16. All I did was square the numerator, which gives me 3. Square the denominator, that gives me 16. So let's substitute that in. We now have the sine squared theta plus 3/16 equals 1. Solve this for sine squared. I'm going to subtract 3/16 from both sides. So sine squared theta, what's 1 minus 3/16? Well, that's 16/16 minus 3/16, which is 13/16. Take the square root of both sides, and we get sine theta. Right now we would say, back to algebra, take the square root of both sides of an equation. Can't forget the plus or minus. We would get plus or minus the square root of 13 over the square root of 16, which is the square root of 13 over 4. But now because I'm in quadrant 2, and I know that the sign is positive in quadrant 2, I can get rid of the plus or minus, because I know I'm in quadrant 2. Is that the same answer we got before as being the sine of theta? Root 13 over 4, right? That's what we got earlier. Just another way of going about it. So now that you have sine, and now that you were given cosine, give me a way you can get tangent. Tangent of this angle, we know, is sine divided by cosine. So we'll take our answer of root 13 over 4, divide that by cosine, which was given negative root 3 over 4. Positive divided by negative is negative. Multiply by the reciprocal, the 4's cancel out, and we got negative root 13 over root 3. Again, we end up rationalizing the denominator just like we did the first time we did the problem, and we get negative root 39 over 3. So notice there, that whole method there of coming up with the correct answer, I didn't come up with a point P, I didn't use, you know what I mean? Just two different ways of coming up with the same answer. All right? So now I'm going to leave it up to you guys for the next 5 minutes or so. I want you to answer or try the bottom problem.
Yeah, I tried that coloring phosphorus thing. Where are you off to?
So there I drew a quadrant 3 angle. Tangent is equal to y over x, which we're being told is positive 4/3. However, we've got to be kind of careful how we label our picture, because negative divided by negative is positive. So I'm in quadrant 3, which is telling me x is negative, y is negative. So if you were to pick a point down here, some point P, just know the coordinates are not 3, 4. It's actually negative 3, negative 4. And then now if we find our r value using the first method I shown you, r is equal to x squared plus y squared, square root of that. We get an r value of 5. And now we're ready to find out whatever they want me to find out. The sine would simply be y over r. Y is negative 4. R was 5. Answer negative 4/5. Should sine be negative in quadrant 3? Yes. Cosine would be x over r. So that's a negative 3 over 5. So in some cases, folks, even though the author wants you to use those Pythagorean identities, in my opinion, going back to the first way we saw to solve these types of problems is just as easy as using your Pythagorean identities. Okay? You guys have any concerns so far?